Hi, everyone. Welcome to the first session. This is one of two sessions on masking techniques. And our first speaker is Funjae Ji. And he's going to talk about, pre-processing, masking with pre-processing. Yes, go ahead.
Thanks for the introduction. This paper is about efficient private circuits with pre-computation, joined with Weijia Wang, Juelin Zhang, and Yu Yu. First, let me introduce its background knowledge. Then I will introduce our new masking multiplications with its formal verification. Next, I will show its application. The final part will be the conclusion. Side channel attacks are based on physical characteristics when the cryptographic algorithm is running. It is feasible because there are correlations between sensitive data and side channel leakage, such as electric power consumptions. A masking scheme, sometimes called the private circuit compiler, is the well-known countermeasure. Its basic idea is to remove the correlations, giving a security order D. Each secret variable X is split into D+1 shares, and using some random variables, and each share is independent of the others. In Boolean masking, which is the most commonly used technique, each share is finally XOR together to reveal the sensitive data X. So a masking scheme is sometimes used in a security model called deep-probing security model. In this model, it is required that this model assures us that an adversary can probe up to D probes at a time. So to achieve deep probing security, it is required that any set of at most D probes is independent of sensitive values. In the masking scheme, the original logical gates, such as XOR gates and AND gates, are often transformed into its masked version. They are called gadgets. They have the same functionality. So people will naively prove each gadget's security and expect the composition to be still secure. But the composition may break probing security oftenly. The composition of deep-probing secure gadgets may not be deep-probing secure. But luckily, we can rely on several security notions that support the deduction from small gadgets to the complete circuit. One of these security notions is called probing isolating non-inference, or PINI for short. Let me briefly introduce its idea. If a circuit with D+1 shares is entirely composed of share-wise gadgets, such as XOR operation, then the whole circuit is split by a D+1 shares that are not interconnected. So it is probing secure because an adversary can only probe up to D shares without knowing the information about the last share. So the PINI notion keeps the intuition and let the nonlinear part behave as if they are not they are not interconnected among these shares. So Piney enjoy powerful and simple composition notions that any composition of Piney gadgets is Piney, which also implies problem security. Another important notion is that any trivial linear operation is Piney. This is useful for block ciphers with numerous linear operations. So to explain the concept of masking scheme, I will show the classic ISW multiplication, which is a generic approach to secure computation. We want to calculate that z equals x times y, and each variable consists of 3 shares. The first step involves the computation of all outer products xi times yj, and in the next step we carefully XOR them with randomness to make sure that it satisfies the problem security. The original ISW multiplication use around d square random bits, and it runs in quadratic times. So our motivation is to make it more practical and efficient, reducing its overheads. Now let's look at the pre-computation-based design paradigm used in our scheme. Typically, a process of masking encryption is inseparable, requiring input data from the initial state. But our paradigm can reassure us that most intermediate variable can only determined by randomness. The whole process is composed of 2 phases, the pre-computation phases and the online computation phase. In pre-computation phase, it takes only randomness for input and produce D shares of ciphertext. It also produces some pre-computed values. Then in online computation, it takes D plus 1 shares of plain text and key and produces large share of ciphertext. Such a paradigm can be used in various scenarios, such as challenge response authentication protocol, which is useful in communication technology. In this protocol, the server use a random value and sends it to client as challenge. The client encrypt the random value and sends the ciphertext back to the server as response. And the server encrypted the random value and checks if the ciphertext is the same as the response. So the pre-computation phase can be done during the idle time. The server and the client can pre-compute some values before the challenge or response arrives. Once the client receives the challenge, he can just encrypt the random by executing online phases. So it can accelerating the communication process significantly. So here is an example of how to use this paradigm. In this case, 3 gadgets are used. multiplication, addition, and refresh gadgets. Each gadget is split by two phases. In pre-computation phase, in pre-computing phase, the paradigm relies on the fact that we are not supposed to know the secret values. So we use refresh gadgets for each input value. Each refresh gadget take no inputs and produces output shares with index 1 to D. And then each gadget is evaluated. They take input shares with index from 1 to D and produces output shares with index 1 to D. For multiplication and addition for multiplication and the refresh gadgets, they produce some pre-computed values. But it should be noted that for addition gadgets, they do not produce pre-computed values because they are just share-wise addition, share-wise operations. Then in the online computation phase, each refresh gadget takes all share of each input variables, and it produces output shares with index D. Then each gadget is evaluated in the same order. Now I will present our new multiplication gadget with K shares step by step. It takes X1 to XK and Y1 to YK as input shares and returns Z1 to ZK as output shares. K is less than or equal to D plus 1. From an overall perspective, it is composed of two parts. The multiplication part with K minus 1 shares and the computation of ZK, forming a recursive structure. The multiplication with K minus 1 shares is called firstly to compute temporary values U1 to UK minus 1. Then in the process of computation, ZK random variables R with index 1 to K minus 1 are generated and used as output shares Z1 to ZK minus 1. Then the ZK is calculated using Z1 to Z minus 1 and some temporary values calculated before. During the whole process, we carefully arrange operations orders to satisfy Piney definition. Each output probe gives knowledge of at most one input shares in the same index as the output probe. And each internal probe gives knowledge of at most one input share. So first multiplication with the K minus 1 shares is performed, and we get variables U1 to UK minus 1. The sum of them covers outer products of X and Y with index 1 to K minus 1, which are painted in blue here. Outer products that not covered now are painted in gray. Then the computation of Z with index K begins. Each R1 to RK minus 1 are generated, and each UI is added to this fresh randomness. Now this tilde R is determined by order products of X and Y, and the random variables. Then we need to calculate the SI, which covers all the products xi times yk. But it should be noted that a prob on the products xi times yk here violate the Piney definition because it requires the knowledge of two different indices. So to solve this problem, we use the variable tilde ri to mask xi and yk respectively. Next, we want to calculate ti, which covers a new product xk times yi. So the same process is followed, and we use si to separate xk from yi. After iterating k minus 1 times, we get ti to tk minus 1, and each ti is determined by the product xi times yk. Finally, these ti's are summed and added to xk times yk, producing zk as output shares. The random variables R1 to Rk minus 1 generated before are regarded as Z1 to Zk minus 1. The main advantage of our new scheme is its suitability to the paradigm mentioned before for k equals d plus 1. The pre-computation phase covers the recursive part. It takes d shares of each input and produces d shares of the output as well as some pre-computed values. It should be noted that d shares of each input are produced by the refresh gadget mentioned before, so that pre-computation phase is only determined by random variables. This phase runs in quadratic time, producing d values and requires around d square random values. The online computation covers the computation of the d plus 1. This phase is much more efficient than pre-computation. It just takes the last share of input and some pre-computed values to compute the last share of output. This phase runs in linear time without random variable. Manually checking high-order mask implementation is not easy, and some errors have appeared in previous papers. So in addition to providing manual proof, we verify the implementation with formal tools, making our proof more concrete. The recursive structure significant benefit the fast verification, which helps verify a larger order of our masking scheme. We assume that the multiplication with d minus 1 share is Piney, and just attempt to verify multiplication with index d is Piney. Variables in multiplication with d minus 1 is just consist a big part of all variables, but it do not need to be considered. We perform a validation using two tools separately. First, we develop our own tools that is customized for the gadget. The verification can be completed until the security the security order 16, while known tools can only verify the multiplication gadgets up to order 12 at best. We also use the popular tool Silver. The verification can be completed until the order 5, which is the largest secret order that can be achieved for a multiplication gadget using Silver. While our gadget is theoretically proven secure, but implementing it correctly in real-world things is not an easy task for cryptography engineer. Typically, it is assumed that the physical leakage of each share is independent of the others. But in real-world implementation, micro architecture in modern processors often breaks the assumptions. In software implementation, transitional leakage is the most common issue, and it comes from register reusing. The actual leakage no longer depends on one share, but it combines two values that are consecutively stored in the same register. So to prevent this issue, we clear temp register by assigning 0 values when necessary, ensuring that one register always load at most 1 share. Our masking scheme is suitable for ciphers using the bit slice technique, which is efficient for software implementation. We compare our results with various state-of-art implementations. The results show that our scheme gains a significant speed up in both pre-computation phase and online phase. At the same time, the requirements for RAM size is smaller, making our scheme more practical in embedding the platforms. Besides, our AES is much faster than the table-based method. We cannot give a fair benchmark for skinny because our implementation is the first higher order masked skinny in software. We also provide t-test results. There does not exist any first order leakage with d equals 1. The phases of pre-computation and online computation is marked in the figures. Even if the randomness is off, the pre-computation phase has no leakage. It is because the secret variables are refreshed and the variables in this phase are all independent of them. So in this work, we provide a new masking multiplication suitable for the pre-computation based paradigm. It is efficient and easy to use. Besides the security proof by hand, we provide the formal verification and the t-test practical evaluations. It is applied to the software implementation of bit-slice AES and Skinny. The performance shows that our results, our new scheme contributes to a significant speed up. Thanks for your listening. Any questions?
Thanks for your talk. We don't have any questions on the Zoom chat yet, so we have time for 1 or 2 questions from the, yes, Emmanuel. The microphone is coming.
Thank you. Thank you for the presentation. Did you compare what you are doing with an approach consisting in recursively implementing ISW?
You mean
the ISW multiplication that you described during your talk? if we wanted to implement it recursively, it's possible just by computing the matrix
You mean
recursively.
the ISW multiplication with pre-computation diagram?
No, without pre-computation, just yeah, it's just an open question. Did you consider comparing what you are doing with just starting directly from the ISW multiplication, but implementing it recursively? So increasing the size of the matrix.
Our scheme is efficient than the ISW multiplication, so we do not compare.
Okay. No, my question was just because the TI that you are processing as a very looks during the multiplication is very close to the form of the TI intermediate results that we have also in the ISW multiplication. But okay, let's discuss that.
It's an interesting question, but maybe I do not catch what you say.
No problem. No problem. Thank you.
Is there any other question if it's a short one? Okay, I don't see anything, which makes us gives us the red light for the next talk. Thank you, Funjay. Our next speaker is Francesco Berti, and he's going to talk to us about parallel masking gadgets.
Hello, where are the slides? Thank you for the nice presentation. I will talk about this paper about parallel gadgets and. Okay. Okay, sorry. Yes, okay. And this is a joint work with Maximilian Hort and Sebastian Faust. And so we have Alice and Bob who wants to communicate, and they wanted to send a message, but they want to send a message, but there is an adversary as usual, and the solution is to use crypto. So both they have a key, in our case it's symmetric crypto, but the adversary can also has physical access to the cryptographic devices performing the computations, so they can so she can measure physical quantities involved in this computation. For example, this is the instantaneous power consumption of a cryptographic computation, which seems not to give so much information, but when I tell you that if the qubit processed is 1 or 0, the shape is different, you can easily read the key. So leakage poses a serious threat to symmetric crypto. Against leakage, there are many countermeasures. The most popular are shuffling and hiding, but in this talk, I will talk about masking, which is the much more used countermeasure. The idea is that we have a secret and we split it in many shares, x0 till xn-1. And in this talk, we will use arithmetic masking, which means that the sum of the shares is the secret. And then we need to do computations on the shares. So to do computation on the shares, we will use gadgets instead of gates to perform the computation. Our objective is to find simple parallel gadget for additive masking, and then prove that they are secure in the random probing model in the presence of leakage. So in this talk, I will talk about a bit of the background. Then I will talk about our security technique, which is leakage diagram. First, I will apply to the refreshing gadget, and then for general circuits. And finally, we give a nice result for the ISVW multiplication. So I will start with the background, talking about masking gadgets and refreshing gadget and the security model for leakage. The idea, as I already said, the idea for masking is to split sensitive variables in n shares, where n is the masking order. To do this, we use an encoding scheme, which is composed by an encoding algorithm, which takes as input a value and outputs n shares of this value. And the decoding algorithm, which takes as input n shares and output the value. We want correctness, which means that the encoding of a value is the identity. And in particular, also to have security, we want that n-1 shares of X are independent from X. In our talk, we will use about arithmetic encoding, which means that the decoding algorithm is simply the sum of the shares. Now we have these shares, and we need to do computation on these shares. We use a circuit model where we have wires, which carries values, and gates, which performs arithmetic computation on wires. But now we have no more values, but we have shares. So we need to compute on them. And for this, we use gadget. We have a gate, which performs an arithmetic operation F with some inputs, and we replace it with a gadget, which works on encodings of the inputs. We want the correctness, which means that the coding of the output shares of the gadget, where the input are encoding of the inputs, is equal to the real output of the gate without any masking. In our talk, we will use a parallel addition, which simply takes as input an encoding of A and an encoding of B, and outputs the pairwise addition of the shares. We have a constant gate which outputs an encoding of the constant, a random gate which outputs random values. For copy, we simply copy the shares. The multiplication gadget, we will see it after. Between gadgets in our work, we need refreshing gadgets for security proofs. The idea is that we have shares, and not to use them too much, we refresh them. So we take some old shares and we create new shares. We want clearly that both the old and the new shares mask the same value, and we want that the new shares are independent from the old shares. In our talk, we use this refreshing gadget, where we add to each share a random value, and we subtract Ri-1 to this random value. So this is parallel because all this computation in the for can be done at the same moment. And this is better because it's more efficient, and we can also, it's also improve the security against side-channel attacks. And we will use this work. In this way, I have given you all the gadgets for every possible arithmetic gate, and I have given you the refreshing gadget. So we have a compiler, which means that we can transform any circuit in a masked circuit. Now we want to assess the security, and there are many possible models to assess the security of these compilers in the presence of leakage. I remember that masked circuits, they work in this way. We encode the inputs, then we compute on the share with gadgets, then we have the output shares, which are decoded. In many models, and also in our, only the computation on the gadget is assumed to leak. Both the encoding and the decoding are assumed to be leak-free. In our talk, we will use the p-random probing model, which means that the adversary can probe each wire with probability p. Probe means that the adversary can obtain the value that a wire carry. Security means that we can simulate the values that the adversary can obtain without knowing the input, except for a negligible probability. The p-probing random probing model is our model. There is another model which is maybe more adherent to the reality, which is the noisy leakage model, which means that the adversary obtain a noisy version of the values carried by each wire. There are nice theorems which connect these two models. The p-random probing model, security in the p-random probing model implies security in the noisy leakage models. So now we can talk about our security technique, which is leakage diagram, and I will explain it for the parallel refreshing algorithm. We start using an idea which was published at AsiaCrypt in 2019 by Zembowski, Faust, and Zabrowski. And the idea is that we need a way to represent the values of a computation and also the intermediate values and how they are related. So we use label direct graph, which means we are using graph with arrows, and they are each edge as a label, which is the set of variables which are represented by this label. The idea, okay, we start for masked value, we put all the shares on a circle, as you can see here. And for other values, we organize that in a way such that if there is a loop, there is a relation between these variables. To make you understand what we are doing, I will give the dependency graph for the parallel refreshing algorithm. As we see, there is the input encoding, so we put a circle. Then we have the output encoding, so we have another circle. Then we have these R values, and so we put them as vertical edges to form the lateral surface of a cylinder. And okay, they form a loop, but this is coherent with our definition because there is this algebraic relation between xi, ri minus 1, and yi. Now we have this bj to represent, and we put on the diagonals of these rectangles, which we have formed before, which again is coherent with the arithmetic relation which they are written down. In particular, since we are considering not a full cylinder, but only the lateral surface of the cylinder, there is a hollow inside. In the next of my presentation, usually instead of using the cylinder, it is easier to represent with the cylindrical projection, which means we take out one edge and we put on both extremes, the left and the right extreme, but they represent the same edge, as you can see also on a planisphere for the Earth. Now I will present the leakage, what we can do with this dependency graph. Often the key point in security proofs is to find when the leakage values can come from two different inputs, because when you can prove this, you can everything else follows easily. And so we define, okay, we have some values that are leaked, and we define the leakage diagram as the subset of the dependency graph, which is formed by the edges whose label contains at least one of the variables which are leaked. So, for example, this is the dependency graph of p-refresh, and suppose that we have all the shares, the input shares leaked. Clearly, this is not secure because you leak the input, but you can see that it forms a loop around the cylinder. Again, if, for example, we replace, we leak all input shares except x2, but we leak r1, r2, and y2, since again, we have a loop around the cylinder, and again, it is insecure because you can recover from R1, Y2, and R2, X2. So again, it is insecure. Instead, if you leak all variables except X4, Y4, and B4, again, in this case, we do not have a loop around the cylinder, and this is secure because we can easily replace X4 with X4 prime, which is X4 plus delta, B4 with B4 plus delta, and Y4 which is y4 plus delta. In this case, we are refreshing a different value. On the other hand, for example, if we leak these values, we are secure and we do not form a loop. But if we add this edge, which is the same, we are again secure and we form a loop around the cylinder. On the other hand, clearly this, which still forms a loop, this leakage diagram, but it is secure because it's independent from all shares except X1. So we have, the idea can be, okay, the leakage is secure if the leakage diagram corresponding to this leakage does not orbit around the cylinder. Okay, we have this idea. Now we want to use this to give proofs and to give security proofs. Here again, we have an example of a leakage diagram. We can observe, okay, in this leakage diagram, there is a gap, which means that there is a set of edges which are not in the leakage diagram, which connects the bottom encoding to the top encoding. This is called the gap, and we can shift the values from a refreshing of x to a refresh to x prime, simply modifying the edges on the edges which are on the gap. In this case, we add delta to xk and yl, and we subtract delta in this case. In this case, all the values can come from a refreshing of x prime. Okay, to give the formal proof, what we have to do is to classify all the gaps and then compute the probability that the leakage diagram orbits. In this case, we use an idea from Zembowski-Talius 2019, which says, okay, if the leakage diagrams, we need at least to have n consecutive edges. And we can easily bound the probability that we have n consecutive edges in the leakage diagram by 9p elevated to the nth power. This is better bound with respect to that work because we are using p and not square root of p as them. Now, okay, we have done security for a single refresh, but we need to have, maybe you can have multiple p refresh one after the other. First, we need to give the dependency graph, okay, and now we observe, okay, each p refresh has a dependency graph which is a cylinder, and we can observe that the top circle of the bottom cylinder contains the same variable as the bottom circle of the top cylinder. So we can glue them together, and so we have the dependency graph of the composition. Again, this is an example of a leakage diagram, which does not orbit, and so there is a gap, as you can see. And we are able to shift make the missing edges, which are the edges of the gap, compatible with input X prime. We can do this. In particular, note that if we consider example, we have these gaps, which are between an encoding on a single P refresh, which are gaps which we have already seen before, but we have these particular gaps which are different because you start from the bottom edge of a P refresh and you go back again to the bottom edge, and this from top edge to top edge. To modify, we can observe that we add here. Then when we have to go down, we subtract delta. Again, since we are going down, now we subtract delta. Again, we up delta because we are going up. And so note that on each encoding, we are adding exactly one time, we are adding delta. For example, on the third, we have plus delta, minus delta, plus delta. Again, for the proof, we need to classify all possible gaps and compute the probability that the leakage diagram orbits. And note that we are giving a global property for the leakage and we are not composing local properties, which in our case gives better security. Now we'll talk about the security of general circuits, and we start with the parallel multiplication SVW and its dependency graph and its security. Here it's the multiplication gadget, which is the normal ISVW, except that the final addition is done in a parallel way. In this way, we have less depth. For its dependency graph, we take a circle, and inspired by the original security proof from ISVW, we put on as a label for the ith edge, the ith input and output shares, some multiplication, some internal values. Note that we have a problem that the values IA, BJ, and BI, AJ both belongs to the ith and jth label. So if we need the probability that an edge is leaked independently from each other, we have to use this, and we want to make it independent, we have to use this formula. And so the parallel ISVW is secure, it's proofed in the paper, if not all edges are leaked, and so we have this security probability. Note that we do not use this normal approximation, and you will see in a few slides why after. For composition, we observe that all our edges are either, all our dependency graphs are either cylinders or circles, and often and always we have that shares of the top or bottom circles of a cylinder are the same in another circle, so we can glue them together. For example, here we have the dependency graph where we refresh the input X and Y, then we sum them, and then we refresh the output shares. Here it's more complex. And again, we can prove security if the leakage diagram does not orbit. And to give the proof, we classify gaps, we do the shifting from input X to X prime as done before, and we compute the probability that the leakage diagram orbits. We have this security for affine, which means no multiplication gadget, and for arithmetic. To conclude, I will give a result for the ISVW multiplication, and in particular, I have to explain you why we have not used this approximation. The idea is this: if you consider this, for example, for n equal 10, this approximation is very well for when p is near to 0, but here you see that we are losing a lot of space. When we elevate it to the nth power, we lose even more. This allows us to use the normal from the security I given before, using some analysis to prove that the compiler we have produced is secure for any leakage probability where the magnitude is 1 over square root of n. And this also works for normal ISVW multiplication. To compare with other works, we can see that in our work, which are the solid line, we are much better than the DFZ paper, because which was the dotted line. And there are other works which try to prove security with random probing composability, which is a property of a gadget, and you can also compute it automatically. And we can have there is different, and for example, they will not work for our compiler. And there is the probe distribution table work from Cassie and Etalius, which gives a tight analysis of what wires are needed to simulate. But the problem is that these tables grow exponentially with the masking order. So as open problems, it's the problem to find dependency graphs for the addition and multiplication, which are better because we are putting so many variables on the same edge. It would be nice to avoid this. We also need to improve the computation of the probability bound at the leakage because our estimation is really, really rough. And it could be nice to apply these techniques to other leakage models or other gadgets. To conclude, we have proved that it's possible to prove the security of a compiler, finding a global property for the leakage and not only composing local property like SNI, PINI, and so on. We have translated the security and insecurity of a leakage in a graph property. And we have improved the result from the AsiaCrypt 2019 paper. Our gadgets are really, really simple, so they are also easier to mask with higher orders. They are all parallel, and in particular, I would like to note that our parallel refresh gadget is not secure in the probing model when 2 wires are leaked. Finally, I would like to tell you that the ISVW compiler is secure in the random probing model if P is as the magnitude of 1 over square root of P and not 1 over N. Well, sorry, P 1 over square root of N and not 1 over N. This concludes my talk, and I'm open for questions, and I thank you for your attention.
Thank you, Francesco. And we have plenty of time for questions. There is no question yet on the chat, so let's look at the room. I'll start with one myself. So I'm curious if we now step away from all the graphs and just look at an AES implementation, what has this work changed when you implement AES compared to before?
Simply that you can have okay, I don't know the slide.
The slides
But you take we have proven better results for the AES if you use an ISV type of masking.
What do you mean by better results? Like area, I mean, no, it's software. So speed,
No,
randomness,
security.
or better security?
Better security because if you took ASVW from previous work, it is 1 over N.
It was not secure enough for?
No, the probability, you need to have the leakage probability, which goes down as 1 over N. And instead here, it goes down as 1 over square root of N.
So what does that mean in practice? Like you need more noise?
No, you need less noise.
For you, before you needed more noise.
Or you need no.
Okay, thank you. Any other questions? I see one hand in the back there.
Hi, yeah, well, thanks for the talk. Do you have performed any practical evaluation of your gadgets?
Well, okay, our is an asymptotical analysis. We have not looked into actual implementation. Anyway, it's nice to have asymptotical analysis for security of gadgets.
Yeah, thanks.
It's interesting because you have given a bound even if you use 1 million shares and without creating tables and so on.
I saw another hand over there.
Thank you for the talk. So random probing model maybe or can be connected to noisy leakage model. I think in the last line of your slide, you said that it's ISW is secure for this order of square root 1 over square root of N, and it's secure for 1 over N. So what does this imply if you are thinking in the noisy leakage model?
Using the connecting theorems, we have a better result in the noisy leakage model by the same magnitude because there are some translations.
Okay.
And so,
yeah, thanks.
Any more questions? Okay, I think then we can go to our coffee break. Thank you, Francesco.
Thank you.